Hi everybody, welcome to another video in Pre-Calculus section 11.1. Sequences. A sequence is a function whose domain is a set of positive integers. Positive integers or just natural numbers 1, 2, 3, 4, 5 and so on. A sequence is usually represented by listing its values in order. The list never ends, so that is infinite sequence, and usually we use ... to indicate that the sequence go on forever. Right. The difference is that even though we define a sequence as a function, but we do not use the function notation for sequence. For example, if we write the function notation, this is the notation of the function f of n is 1 over n. However, we will use a sub 1 to write the first term. So in the function we write f of 1, but in the sequence we write a of 1 and then a of 2 and then so on. Of course, if it is 1 over n, a sub 1, we're going to substitute 1 in for n, 1 over 1 is 1 and then so on. So the values of the sequence is not important here, but we just focus on the notation. And also we can put all the terms in the bracket to denote a sequence a sub n, or we write a sequence spell out what each sequence is equal to. So it's like that. Right. Now let's write the first 6 terms of this sequence n plus 2 over n. The first 6 terms, so pretty much we will have a1. We're going to put 1 in for n. And a2, put 2 in for n. a3, a4, 6 over 4 is 3 halves, 5, 7 fifths, 6, that is 4 over 3. Of course, if we use the calculator, hit mode function, we did use parametric and polar. Now go to sequence, and then we would write sequence. The first term is 1. The first term we start with n, so we start with a1. Use of n equal to, just say n plus 2 divided by n, and we just go to second table. You'll see I can even do the simple math. Right. So of course we can just do this. His variable, y variable, and this is, can we have sequence? Nope. Look for the u. Okay. Yeah, that works. Yeah, we just hit second u because the sequence here is in terms of u. So if we just hit second u, and then we want the first 6 terms, so we open the bracket 1, 2, 3, 4, 5, and 6. close the curly bracket, and that the first 6 term change to fraction, and that's what we have. Right. Same thing here. For the first 6 term of the sequence, we start from 1 and then so on. Put 1 in for n. So negative 1 to the first power is negative 1/2. B2, negative 1 to the second, 2/2. So 1 and 1 is 1. So if we put in the sequence instead, we have negative 1, raised to the n power of n/2. And then once again we want the first 6 terms, change that to fraction, and of course keep doing that. We have B3 is negative 3/2, B4 is 2, B3 negative 5/2, B5 B 6, 3. We just keep doing that. Right. Now determine a sequence from a pair. 1, 3, 9, 27. Okay, it is easy to determine. The next term is going to be multiplied by 3, right? So can we just multiply by 3 to get from this term to the next, and multiply this term to the next? So to write the sequence, we will say it's going to be 3 times something. But if we just keep multiplying by 3, think about this. The first one, we don't have 3. The second term, we have 3. The third term, 3 times 3. The fourth term, 3 times 3 times 3. So pretty much we're going to have n minus 1 terms. Right? Because when the first term, when n equal to 1, we have 1 minus 1 is 0, 3 to 0 power is 1. After that, we have the number of factor of 3 will be 1 less than the term itself. Or we just hit second table, and then we see the sequence over here: 1, 3, 9, 27, 81, and so on. So that is correct. Once again, the first term, we have 1 number 3. The second term, we have 3 times 3. That's right. 3 to the first, 3 square. The second term. The third term, the second term we have 1, 3. The third term we have 2, 3. The fourth term we have 3 times 3 times 3, 3 cubed. As you see, the number of terms, the n, is 1 more than the power itself. So that's why I subtract 1 there. Right. Now we have this 1/2, 1/4, 1/8, and 1/16. Same thing. We start with 1/2, right? So A1 is 1/2. A2, 1/4. Can we write as 1/2 times 2, or 2 square? A third, 1/8, which is 1/2 cubed. If we write in this pattern, essentially the n term is equal to 1 over what? All of them under 1, right? First term to the first, second to the second, third term to the third. So the n term is equal to that. Of course, we can check with the calculator. Or of course, we can also write 1/2 all of that to the n power, which is perfectly fine. Right. Next we have 1, -2, 4, -8. So it's easy to determine, easy to see that the sign alternating. So the first term is 1. The second term is -2. The third term is 4. By the way, 4 is 2 square. -2 to the first, and 8 to the fourth is -8, which is -2 cubed. Now if we talk about in relation of the index, which of course 1, you can also write 2 to the 0 power. So watch for those index and watch for those power. What do we see? The index has 1 more than the power, right? So we say a sub n. The index is 1 more than, so we have to subtract 1 here, because that index is 1 more than the exponent. Now we have the -1, the sign alternating. How do we do that? So to take care of the negative, we're going to have -1 raised to some power. If it is an even power, it's going to be positive. If it is odd, it's going to be negative. Alright, so we look at this. The first one is going to be even. So if we start with 1, it cannot start with 1. It has to start from the even number. So we can start with 0. And then this -1 to the first. So pretty much this also -1. And if we put n, we start with 1, and that's going to be negative. It doesn't work. So we have to either +1 or -1. I could do +1 or I could do -1. Because in that case, the first term with n equal to 1, 1 minus 1 is 0, -1 to 0 power is 1. So to guarantee the first term positive, we have to use the -1 to n minus 1. And that gives us the sequence of generating that sequence, the formula for that sequence. Right. We can also write a sequence in recursive formula, meaning that this term depends on the previous term, and then so on. So, for example, we can write out the first 5 terms of the sequence recursively based on this. So we know the A1 is 2, and then we said by the first 5 terms we have the first term is A2, A1 is 2, A2. We're going to put 2 here and here. 4 plus A up 2 minus 1. 4 plus A1 is 2. It's going to be 6. A3 is going to be 4 plus A. If you put n here, 3 here for n, 3 and 3. So we have 4 plus A2. A2 is 6. And then we just keep doing that. By the way, we can put that recursion formula in the calculator. We start with 1, and here A1 is equal to 2. Right. After that, the recursive is that we have 4 plus, and then we have to use u second, and that number 7, and then we enter n minus 1. Alright, and then go to the table. Right, have 2, 6, 10, 14, and 18, and 22. Pretty much we just add 4 to get from this term to the next, and of course just keep doing that. A4 is going to be 4 plus A of 4 minus 1, or 4 plus A3, 4 plus 10 is 14, and of course we can just keep going to the 5th term. Right, we can use recursive formula to define factorial. Factorial and factorial meaning it is a product from that number all the way back to 1. 0 factorial is defined to be 1, and 1 factorial trivially is 1. Right, so what is 5 factorial? Will be 5 times 4 times 3 times 2 times 1, and that is 120. Right. Now, try to simplify 9 factorial over 7 factorial. By the way, in the calculator, if we want factorial, it is math, go to that probability tab, option number 4. So for example, 5, math, go to that tab, option number 4. Right. Now if we want to do this by hand, 9 factorial meaning 9 times 8 times 7, 6, 5, 4, 3, 2, 1. And 7 is 7, 6, 5, 4, 3, 2, 1. Notice that we can cancel the from 1 to 7. We have 9 times 8, which is 72. By the way, this is not the best way to do it. The best way to do this, the reason we use this notation is that from 9 we can write 9, 8. If we want to stop, we just put the exclamation point there. But this time we stop at 7. And we can stop at any number. From 9, 8, we can stop at 7. If we want to go down to 7, 6, then we stop. Every time we stop, just put the exclamation point there. And then it's easy to see that this cancel out at 7 factorial. And 9 times 8 because 72. Right, the next part is the summation. Summation is the sum of the terms in the sequence. Right, for example, we write A1 plus A2 plus A on the way to A sub n is the summation when k go to 1 to n. So we have the index here changing from 1 to n. So we go from 1, 2, 3. So when we write the summation, we go from the lower limit to the upper limit, and it is increased 1 every time. And that is called the sigma, or the Greek capital letter sigma, which is in capital S, uppercase S. Right, let's see how it works. Find there will be a formula, so let's just make things simple. Make this a 5. Write out the sum of this 1 to 5 of k squared. So simple, we just put 1 in for k, 2 in for k, 3 in for k, 4 for k, and 5 for k. And we do that, we have 1 plus 4 plus 9 plus 16 plus 25. So that is 25, 25, and 5 with 55. Right. If we want to use the calculator, by the way, not every calculator can do this, but if you're using the TI-84, and when you hit math, and if you go down to, and there's the option that say summation, and we use that. And let's say n go from 1 to 5, and here we have n squared. Because that indeed is 55. Right. Also, let's put some numbers here. Let's put this 6. This is summation of k go from 2 to 6 up 2 over k. So we just put 2 in the lower limit first, and then just keep increasing until we have the upper limit. So we just do that, or we use the calculator. Summation that goes from 2 to 6 up 2 over k. We use n. Convert that to fraction, 29 over 10. Right. So it's simple enough. Now the opposite direction is not as trivial. Rather, some using the summation. Right. So we're going to have the summation. Right. Let the index be k, equal to something, of something. Right. Now, in order to do that, we have to recognize the parent of the term in the sum. We can say 2 to the first, right? 2 square, 2 cube, 2 to the fourth, all the way to what? 256 is 2 to the 8. So we sum all of that. The common part of all of this is the base of 2. The part that's not the same are the exponent. That go from 1 to 8. So that's how we develop the parent, like that. Right, this one, 1/3, 2 over 9, 1 over 9. Now that's confusing. If this is 3, then this makes sense. And in fact, it makes sense if we just multiply 3 top and bottom. So instead, we will have 1 over 3 plus 2 over 3, 3 over 27, 4 over 81, and 5 over 243. Alright, how do we write 2 over 9? The summation. We have to write something in common, the common parent of them. We can say 1 over 3, 9, 27, 81, 243. Those look like the power of 3, and it is. And we can see that it go like that. So the top number change from 1 to 5, so we can say k go from 1 to 5. At the bottom we have 3 to those power, the same as the top. So that's what we have as summation. Right, here we have some properties of summation. We can, if it is a constant, we can take it outside. Summation of a sum is the sum of the summations, and then this will continue the index. We go from j minus 1 to n, is we go from 1 to n, and we take out 1 to j. So if we want from k equal to j minus 1 to n, this one j minus 1 and this one j, and this is n, this is 1. So instead of go from 1 to n, we take out from 1 to j. This will be a plus. Right. Let me just write out the slot. Okay, the slot 1, 2, all the way to j. The next one, of course, j plus 1, and the last one is going to be n. So if we're going to count everything from 1 to n, that's fine. But if we take away from 1 to n, and then we take from 1 to j, of course we have j plus 1 to n, and that's what the formula is about. Next we have the formula for the sum of all the constant. C is going to be c times n. N is upper limit, go from 1 to n. The sum from 1 to n of k, if we have the sum of k, meaning 1 plus 2 plus all the way to n is n times n plus 1 divided by 2. K squared is going to be that. K cubed is going to be that. Right, now how are we going to use that to calculate this summation that we have here, this example? Right, so simple enough. First thing we can do is we take out the 2, because the constant we can take it outside. And then next we use this formula, the sum of everything to the first power. It's going to be the upper limit, n times n plus 1 divided by 2. So we're going to have 2, 5, and 5 plus 1 divided by 2. 2 and 2 cancel out, 5, and 6 is 30. Right, so pretty much we use the formula for summation, because if we use the summation formula itself, that go from 1 to 5 to k to n is 30. Right, next we have this. We can split the summation. K square, right? Right, so the first one we have, if it is a constant like what we have in here, 3, it's going to be just this part, just going to take 3 times n. But this is the sum of all the square. The sum of all the square, we're going to use that formula, right? N times n plus 1 to n plus 1 divided by 6. N is the upper limit, so we have 10 plus 1, 2 times 10 plus 1 divided by 6. That gives us this summation. And then the other one will be just 3 times the upper limit. And so we have 10, 11, and 21 divided by 6 plus 30. 10 times 11 times 21 divided by 6 plus 30 is 415. If we enter the sum directly, choose n from 1 to 10, n square plus 3. Yeah, that's what we have. Yeah, so that pretty much all I want to cover for section 11.1. We have a lot of little things. Define a sequence, recursive formula for a sequence, the summation, and the summation notation. And then this formula will come in handy in Calculus 1. That's all I want to cover this section. As always, thank you for watching, and see you in another video in Calculus.